Have you ever just stopped and wondered how we got here? I mean, to a world where you can literally talk to your phone, get a pizza with a few tops, or watch a rocket land itself back on Earth. It all really boils down to one thing: our ability to speak to machines. And this is the story of that conversation, a wild journey full of brilliant minds, fierce rivalries, and just incredible innovation. All right, let's get into it. So, it all starts with this one huge question. Deep down, computers are actually pretty simple. They only understand electricity, on or off, ones and zeros. So how on earth do you take a complex human idea, like, say, calculating a rocket's trajectory, and translate that into a language a bunch of switches can actually understand and execute? This single problem, right here, is the engine that has driven decades and decades of progress. In the very beginning, programmers had it rough. I mean, they had to write in pure machine code. And you can just imagine, it was an absolute nightmare. It was nearly impossible for a human to read, a total headache to modify, and just mind-numbingly tedious to write. So the goal, the big dream, was to create something better. A language that was readable, that was powerful, and that let humans express their ideas without getting completely bogged down in the nitty-gritty details of the machine itself. To really see how we got there, we have to rewind. I'm talking way, way back to a time before the word software as we know it even really existed, a time when the very first abstract ideas of a high-level language were just starting to form. And get this was even before there were a lot of computers out there to run them on. And the ambition was huge, right from day one. Picture this. It's Germany, 1945. Right in the middle of all that chaos, an engineer named Konrad Zuse designs Plankalkül. It was the first ever design for what we'd call a high-level programming language, and he meant for it to be used for engineering. Now, it was never actually implemented, but that's not the point. It made a really bold statement. It said, hey, we shouldn't have to think like the machine. The machine should learn to think more like us. So, next up, we enter the era of the giants. And I mean that literally, the mainframe computers. These things were beasts. They took up entire rooms, they were famously unreliable, and trying to talk to them required a whole new class of practical, powerful tools. This, right here, is where programming languages as we really know them were truly born. And then, in this incredible burst of creativity in the late 1950s, 3 legendary languages just appeared, almost all at once. And what's so cool is that each one was built to solve a completely different kind of problem. For the scientists, you had Fortran. For the brand new, kind of wild field of artificial intelligence, you got Lisp. And to run the entire world of business, there was COBOL. Fortran, which stands for Formula Translation, was a total game changer. It was designed for the IBM 704, one of the first computers that had special hardware just for doing complex math with decimal points, what we call floating point math. See, in an age of unreliable machines, raw speed was everything. Your program had to finish before the computer broke down. And Fortran delivered, producing incredibly fast code that finally let scientists and engineers really harness the power of these new machines. Meanwhile, over at MIT, you had researchers in this new field of artificial intelligence, and they needed something totally different. They needed a way to represent complex, symbolic ideas, not just numbers. The answer was Lisp. And Lisp's core idea was just brilliant. Everything, the code, the data, all of it, could be represented as a simple list. This one elegant, super powerful concept made it the language of choice for AI research for decades to come. And then you had the language that would quietly go on to run pretty much the entire world's economy: COBOL, the Common Business-Oriented Language. It was designed to look like English, to be easy to read, which made it perfect for things like processing payroll and managing records. Its place in history was totally cemented when the U.S. Department of Defense made it a requirement for their projects. And just like that, it became the backbone of government and financial systems for generations. So after these first pioneers proved it was possible, the floodgates just burst open. The next era wasn't just about raw efficiency anymore. No, it was about exploring new ideas, new ways of thinking about programming, and, this is key, making it accessible to way more people than ever before. And this new philosophy is perfectly captured by a language called BASIC. It was developed at Dartmouth College, and its goals were, for the time, pretty revolutionary. It was designed to be pleasant and friendly. Can you imagine a friendly programming language? It was meant to be easy for non-science students to learn, and for the first time, the motto was, the user's time is more important than the computer's time. That one little shift in thinking would define the future. Now, as programs got bigger and more complicated,
a new idea emerged to manage all that complexity. It was called structured programming. You had languages like Pascal that were designed specifically to teach this more disciplined approach to coding. At the same time, over at Bell Labs, a guy named Dennis Ritchie created C. C was a different animal entirely. Lean, powerful, and very close to the hardware. It was built for one huge job, to write the Unix operating system from the ground up.
But the biggest shift in thinking was still yet to come. It was a whole new paradigm called object-oriented programming, or OOP for short. The big idea was to stop thinking about a program as just a long list of instructions. Instead, why not model the real world as a collection of objects, where each object has its own data and its own behaviors?
And OOP was built on 4 really powerful ideas. First, you have encapsulation, which just means bundling your data and the methods that work on it together in a neat little package. Then there's abstraction, which is all about hiding the complex guts of an object and only showing what's necessary. Third is inheritance, which lets new objects inherit properties from existing ones. And finally, polymorphism, which lets you use a single interface for different types of objects. Put them all together, and yeah, these ideas changed everything.
The first language to really embrace all of these OOP ideas was called Smalltalk, and it was developed at the legendary Xerox PARC. And the result wasn't just a language, it was a revolution in how we use computers. The work on Smalltalk pioneered the graphical user interface. You know, the windows, icons, and menus that are the foundation of every single modern computer and smartphone we use today. Now, the next generation of really dominant languages, they didn't invent everything from scratch. Instead, they really stood on the shoulders of giants. They brilliantly combined the power of those older, faster languages with the revolutionary new ideas of object-oriented design. And C++ is the perfect example of this. Barney Stroustrup over at Bell Labs wanted the raw power and efficiency of C, but he also wanted the advanced OOP features from another language called Simula, so he put them together. The result was first called C with classes, and that eventually evolved into C++, a language that would absolutely dominate high-performance computing for decades. Here's a fun little fact about the next major language to come along. It wasn't always called Java. The project over at Sun Microsystems actually started with the name Oak, named after a tree that was right outside the lead designer's office. Then it was briefly called Green, before the creators finally landed on Java, inspired by all the coffee they were drinking, a simple name for a language that was about to change the world. Now, while Java and C++ were focused on these massive, large-scale systems, another language was being born from a totally different philosophy: developer happiness. Guido van Rossum designed Python with this relentless focus on code readability and simplicity. The goal was to let programmers express concepts in fewer lines of code, making it not just a powerful tool, but actually a joy to use. And wow, did that philosophy pay off? Just take a look at this list. It's just a glimpse of Python's impact. It's one of the main languages at Google. It powers huge parts of Netflix, Spotify, and Instagram. Even NASA uses it for scientific computing. It turns out that focus on simplicity made it powerful enough for everyone. And then, of course, the internet arrived. And with it, a whole new universe of problems to solve. It demanded a completely new breed of languages, designed specifically for a world that was always on and always connected. This led to an explosion of what are called scripting languages, languages designed to automate tasks and work inside a bigger system. You had JavaScript, which was created to run inside the web browser and make pages interactive and dynamic. And on the server, you had languages like PHP, built to process forms and talk to databases. They generated the content that JavaScript would then bring to life, and together, they built the interactive web we all use every day. You know, when you step back and look at the whole journey, the scope of it all is just staggering. This quote here was originally used to describe a language called Ada, but it perfectly captures the immense responsibility we've handed over to these languages we've invented. They run everything, from missile control systems to your payroll to the air traffic control that keeps planes in the sky. So think about it. In the span of a single human lifetime, we've gone from physically flipping switches to talking to our machines. The whole story has just been a constant search for a better solution. From a need for raw speed, to a desire for logical structure, to a focus on making things simple for the programmer, and finally, to the insane demands of a connected world. And it leaves us with one final, really exciting question. What's the next fundamental problem that the next great programming language is going to solve?